is a senior Italian forecaster with more than 25 years of experience in the field. So after his master's degree in physics at University of Bologna, he has been employed as a regional weather service of Emilia-Romagna, but with other important work experience. So those of you who have been at TCMWF for a long time certainly remember him when he was a staff member in the operational department as Synoptic analyst in METOPS between 2001 and 2005. So currently, Federico is finishing a 3-year research project at LMU University in Munich on extreme precipitation dynamics. So I'll leave it to you. If you have any question, by the way, we will use a chat box, and then Federico or myself, we will read the question at the end of the talk.
Okay, thank you very much for the invitation and for the presentation. I'm really glad to present at ECMWF, and this is the presentation is about our project that we carried out in collaboration here at the University of Munich, and especially I would like to thank with all these people listed in the first slide that are basically co-authors of this work in the different parts of this work. And as you can see, people are spread in different institutes, Munich, University of Mainz, and also I would like to thank ARPA Emilia-Romagna as a collaboration partner of this project. So what is it? So this project is a transfer project that belongs to Waste to Weather. Waste to Weather is a collaborative research center and is a long-term program founded by the DFG, that is the research institution of Germany. And Waste to Weather is a basic research project on predictability, and divided in three basically main areas that are about fast upscale growth of forecast error, cloud processes, and influence of local factors on weather and extremes. So the transfer project, which we designed, was the aim of this transfer project was to basically transfer knowledge from research in these fields into operation methods that can be applied in forecasting offices. And for this, the application partner is usually for this kind of projects a kind of weather service or an institution that is used to test this concept. And I will say one of the major aspect of this collaborative research centers, like Waste to Weather, is that it can bring together all the necessary scientific expertise from different fields and from different sites. So Waste to Weather in reality is a project that involves 6 institutions in Germany. So the University of Munich, but also the Technische University, University of Mainz, Karlsruhe, Heidelberg, and the DLR in Oberpfaffenhofen. So, okay, this was a kind of general introduction, the framework in which the study of the extreme precipitation happened, and what we wanted to investigate was basically we want to try to see if we could use some concept, some new methodology to address and to improve the predictability of extreme precipitation. And we choose Northern Italy as a target area for this research. And you may wonder why, but I guess you also already have the answer, because Northern Italy, I mean, especially if you look from a user's perspective, it's an area of, it's a region that is very severely affected by these events. I put here in this slide just 3 types of different floods that we can have, and you see we had many floods in the cities. Genova is one of the most famous example. But extreme precipitation can generate also the breeze flows, and especially on the mountain, on the side of the mountains, you can have huge damages. This is the one here is occurred only recently. I mean, just at the beginning of October was this storm that affected South France and Northern Italy, and we will talk about it later. But also floods due to big rivers like the Po River. Why I say floods? I mean, why I show this, because you can also see from this type of effect that extreme precipitation events are not the same, and they can be generated by different processes, and so different type of extreme precipitation can produce different effects at the ground. So okay, another reason so that was more for a kind of user perspective. So that region is really a region when this phenomenon occurs and produce a lot of damages. But you can look also at the scientific perspective, and if you want to test ideas and to try relation and explore the predictability of extreme precipitation event, you have to build a kind of data set that is very rich of these events. So the frequencies is a very important aspect. And as I said before, Northern Italy is really one of the regions in Europe, actually is the region in Europe with the highest frequency of this event. And you can read this nice paper that appeared on Nature Communication, and in which they, for example, investigate the frequency of this event in Europe, and you see that actually more than half of the EU floods, and so also the extreme precipitation, are occurring in only 3 countries, so Italy, Spain, and France. So as you can see, this blue area are really showing basically the Mediterranean basin is one of the regions with the highest frequency, and Northern Italy is the highest in that region. Okay, extreme precipitation, fine, but as I said before, extreme precipitation can be generated by different processes. Although, I mean, some ingredients are common to all the extremes. First of all, you need a large amount of water vapor to flow into your area, and because to maintain an extreme for several to maintain extreme intensities, for example, for several hours on a given place, you need really a strong convergence of water vapor. Otherwise, even if you have a very high amount of total column water vapor, this can be rained out very quickly in an hour or so if you have a kind of a big thunderstorm. So you need really a continuous flow of water vapor into your region. And so one of the main ingredients, we start already to put things on the table, I would say. One of the major ingredients is the integrated water vapor transport Flux. That is kind of integral in the vertical of the water vapor flux into the atmosphere. But then, yes, the precipitation can occur according to different processes. You have fronts and you know, yeah, the mid-latitude fronts and cyclone structures that produce precipitation over a wide area, and you have war conveyor belt inside associated with cyclone. That is a kind of large swath of ascending air, and also and that can produce precipitation over a large area, and also moderate to high intensity. And then on the let's say smaller spatial scale, you have also moist convection, and in particular you can have deep convection that can also produce very intense but localized precipitation. And so you have on the opposite side these two processes, but you have also an intermediate. So you can have also situation where you have fronts and deep convection, and then you have the local enhancement due to different factors, and like the orographic enhancement is one of the principal things. So here it's just to say that we want to go a little bit deeper and try to see if we can not only recognize extreme precipitation, but also classify them and according to the process that is acting in prevalence in each situation. So to do so, so at the base of this investigation, there is the creation of a catalog of extreme precipitation events. Another reason to choose Northern Italy, because the colleagues of the regional weather services, they put together a really nice data set. It's called ARCIS, and is a gridded observation data set that contains daily precipitation from 1961 to 2015, and it will be updated in real time soon. So it's a very high resolution. It's 5 kilometer by 5 kilometer. It's derived from more than 1,500 stations, and at the moment it contains only daily precipitation. So it's a daily data set. And what we did, we used this as a base of our for the creation of our catalog, and to produce and we had to define an extreme. We had to define we had to create our definition for an extreme, and to do so, we, instead of working on single grid cells of the data set, we decided to aggregate precipitation over official warning areas that we use for civil protection purposes. So we average the precipitation over each area for each day, and we define an extreme precipitation events a day in which at least one of the warning area exceed the 99th percentile of the climate distribution. So the precipitation in at least one of the warning area for that day exceeded the 99th percentile of the climate distribution. Doing so, we found more than 800 days, 800 extreme precipitation events in the period 1979-2015. We restricted to 1979 because we wanted to use also the reanalysis to characterize the days. So so we restricted to this. Of course, you can do many analyses. The main analysis, the first analysis we did was to, for example, to simply show the seasonal distribution of extremes over this area, and you see that you have a prominent peak in autumn and a kind of secondary peak also in spring. And so, just looking at this map, you can start to put down questions that you want to try to answer, and the first one I said, can we classify extremes according to the process? Are the frequency and seasonality controlled by the large-scale dynamics, and which implication of this consideration for predictability? So that were our initial research questions, and we will go through this basically during the presentation. So first of all, to classify according to the processes, we need to define a number of predictors that could be useful to characterize the large-scale dynamics. Well, the atmosphere associated to each extreme. And we did so. You can read the detail then in this paper that is just about the classification. And we define, we come up with 6 variables, actually 8 variables that were derived mostly from literature and from also experience of during the forecasting experience, not only myself, but of course the scientific community. I mean, it's pretty normal to use to develop like method to estimate different things, and using proxy in the atmosphere to estimate also surface parameters. But so this is the list of variables, and perhaps, I mean, I guess all are rather known, except perhaps for this convective adjustment timescale that we use to define the type of convection, and according to this timescale that has been described in few papers, especially from the group of George Craig here at LMU, and also when he was in Reading. The convective timescale is it's able to discriminate between a convection that is linked to weakly forced situations, so where the large scale is not so important, to respect to other situation in which the large scale is really driving the convection. Okay, so once defined this list of variables, we used then a simple machine learning approach to, first of all, to create clusters, and using k-means, and then using random forest to have a second, how can I say, evaluation of the importance of all these variables in creating these clusters, and using this property of the random forest, or the estimate of the feature importance, we could in fact remove 2 of the predictors, because we're not basically so useful in estimating the classes. And since we use the k-means, this unsupervised approach, the only thing we had to define was the number of clusters that we wanted. So the number of clusters that and we define this number in 3. Why 3? Because, as I said at the beginning, if you think an extreme precipitation event could be defined according to the type of precipitation that is occurring, we said we have the large-scale precipitation associated with front and cyclone. We have deep convection. These are 2 classes, and we thought to define also a third class that is a kind of in between the 2. So at the opposite edge, we have class 1, category 1, that is precipitation falling in cyclone, mid-latitude weather cyclone. Class 3 is really poorly convective events, and class 2 is in between of the 2 things. This method turns to be successful, so we could produce really 3 fairly well separated clusters. And you can look at the paper. I mean, we did different trials, and basically using this machine learning approach was producing better results than, for example, simply establishing some threshold judging on CAPE, on tau, or so it's a, yeah, I cannot spend too much time on this, but as I said, you can read the details on the paper. And okay, so let's have a look at these 3 classes. So this is the first row. You have the composite of the geopotential at 500, the mean sea level pressure in white, and in shaded you have the integrated water vapor transport. So the first thing that you notice that in all 3 classes you have a trough, and they may look very similar at the first sight. So, but if you look closely, you find differences that are most dramatic in the integrated water vapor transport. So you see straight away that in category 2, that is this intermediate, you have a very strong flux of water vapor into this region. And you see by the scale, the color of the scale, but also you see also, and the wind, sorry, the wind vectors are showing the wind at 850 hectopascal. So in terms of synoptic, you see that the trough in the category 2 is more shifted to the west compared to the axis of the trough of category 1. There is a cyclone over the Gulf of Genoa or the North Tyrrhenian Sea in category 1, while here is more like of north to the Balearic Island. And there is a very one important aspect is that the seasonality is very different in the 3 categories. And you see category 1 are occurring mainly in winter. Category 2 are mainly occurring in late spring and autumn, early autumn. And category 3 are mainly summer, with some overlapping, of course. But this separation in the season is not something that we have designed into in the algorithm. It's simply through this automatic separation clustering done based only on atmospheric predictors. This came out naturally, and this, I think, is a nice also result. And in the row below, you see the composite of the precipitation associated with each category. So you see, you may have, guessed that if you have a lot of integrated water vapor transport, the precipitation intensity is also much higher than the other 2 categories. And also the spatial extension of these events is larger. And we see that, for example, in this plot here, where we see for the 3 categories, the mean area associated with each extreme. And you see that for category 2, this is 10 in 10 to the third. So we are about 10,000 kilometers square. And while for category 1 it's about 5, and for category 3 it's about 6, so it's almost the double the spatial amplitude of these events. And then you can also look at differences in other variables, and this is again is showing up nicely that it's we obtain we obtained what we wanted to obtain. So this nice separation between events associated with cyclone occurring mostly in winter on one side, on the opposite side, summer convection with very high instability, and these intermediate events that, by the way, are perhaps the most important for our territory. Okay, so so we have achieved now this separation. Now we want to see if we would like to really quantify which is the role of the large scale in producing these events, comparing to local conditions or local factors. In the search of some large-scale indicators, we had to build a kind of conceptual thinking to link these extreme events to the large scale. And this has been done for, it's not new. There are many works on this aspect, and one of perhaps the earliest, but maybe not even the earliest, is this from Masakan, Berley, and Davis in which they they found a precursor, an upper level precursor of every precipitation. So we did, I mean, there's been a lot of activity in the literature about this. So we can now build a more like precise connection between extreme precipitation events and large scale. And I will say that we can divide in three parts. So you have the extreme precipitation event, you have the flow that you need to achieve the stream. So really high integrated water vapor transport that sometimes, I mean, it can be called also atmospheric river. Atmospheric river is simply a region of the atmosphere in which you have a really high transport according and above some given threshold. Okay, and this, so the atmospheric rivers is tightly linked to a wave that produce such a strong gradient to induce this flow. So typically a Rossby wave that can be in a breaking stage, like I draw here, or it can be more in a linear transient stage. But anyway, more or less, this is the schema. So going from the extreme, you have the IVT transport, and you have the wave that is associated with the transport is associated with the wave. So if we manage to define a way to recognize this, we can hope to recognize extreme precipitation by the large scale signature. That's the idea of the thing. And so to recognize this, basically the ultimate forcing, that is the one associated with the wave that should be in place to generate the IVT and then the precipitation, we can use different metrics. And in this presentation, we will use the Rossby wave packet envelope and the Pva anomaly. So when you have a wave like this, you have also, can be seen also as a PV streamer. So a kind of exchange of potential vorticity, and this will generate an anomaly compared to a normal climatological value. So you can check for this anomaly, and this is a tracer of PV streamer basically. So that was a kind of schematic, but you can see exactly the same in this last case that I was mentioning before. I mean, this flood that occurred over South France and Northern Italy on the 3rd of October was really extreme. And no surprise that this flood was associated with a large Rossby wave, and on the forward side of the Rossby wave, there was a really strong flow of integrated water vapor transport. And you see this green here is our target area, and you can see that part here is what we can call atmospheric river, because we are well above the threshold for atmospheric rivers. Actually, in a classification that Ralph and Al are proposing, this rank as a between very severe and exceptional extreme rivers. So, and no surprise, we had like 300 and 400 millimeter, even, well, we had up to 600 millimeter in 24 hours in the southern part of France and northern Italy. So IVT is really a good tracer, and also this is not new. I mean, literature is also David Levers, for example, at ECNWF has worked a lot on this. But we will come back maybe at the end if I have time to this thing, to this case. So yeah, so okay, so let's I wanted, so that just to say another example, just to say that we use, okay, So I introduced the envelope of Rossby wave packet and also the Pva anomaly because we wanted to check this relation between the large scale and extreme precipitation. So this is another case, a case in which a famous flood case that affected northern Italy in 1994, when I was really at the beginning of my work as a forecaster. And with the analysis, we could revisit this case in detail. Actually, there was a full workshop on this case in Italy last year. And yeah, so this is a nice showcase in which we could see the principal component that we use for this work. So you have again a trough Rossby wave. You have a strong flow of IVT going into this region, a little bit weaker than the last one, and you can trace it back in this kind of view back in time. And what you follow, I mean, these black lines are the envelope of the Rossby wave packet. So basically, you take the wind, you take the meridional component of the wind at jet level, and you compute and you take the anomaly of the meridional component. You compute the envelope of this anomaly, and you are able to follow the downstream development associated with the propagation of energy from one system to the next one. And so, and you're also, so if you go back basically in time, starting from this trough, you follow the propagation of the energy through at the jet level, and in this case, you end up in the Pacific. So there is this is simply to say that there is a propagation from upstream of energy that produce downstream development and finally put in place the trough that generate precipitation. This is also to show that we can really trace back a kind of, well, actually we try to trace back a single phenomena to a kind of global perspective. But going back for a second to this, again, water vapor transport, and we can also characterize the different categories of our extremes in the distribution, looking at the distribution of the water vapor transport. In this case, we look only at the meridional component, that is the most important for the northern Italy part. So when you have flow coming from the south, it's bringing a lot of moisture, not only from the Mediterranean itself, but also from furthest west from the Atlantic. And you see that the distribution of the three categories is different, with category 2, that are the most extreme, more shifted on big values. And when you have no extremes, you see that the meridional component is pretty almost zero. Basically, you have so this distribution are fairly well separated, and this lines are many famous events, especially in the Italian forecasting community, of course. That affected our region recently and also historically. So I put here also the Piedmont case that we just analyzed. So you see that they were mostly falling under this distribution of category 2. You may have heard about Storm Vaya that destroyed all these trees and produced floods and high water in 2018. It was really an extreme in terms of transport of integrated water of water vapor, but Alex was just slightly lower than this. So yeah, I mean, I guess this in the future perhaps will, I guess there will be a tendency of increasing, of course, of water vapor transport, and then it's also very important to monitor this quantity, not only for prediction itself, but also in terms of changes in the climate. But going back to our relation, now we can, using these two indicators, so the envelope of the Pva anomaly, we can now measure somehow the relation between the large scale and the precipitation. In particular, we can compute the probability to have an extreme events over our northern central Italy domain, that is more or less this one, according to the amplitude of the Rossby wave packet. And you see that there is a kind of direct relation between envelope, so Rossby wave packet amplitude, and probability of having an extreme precipitation. So this the envelope has been computed over a slightly over an area that is more to the west, because as I pointed out here, you see, compared to the extreme precipitation, the maximum of the envelope in this case is about here. So you have to look a little bit more to the west, and here you have another matrix that is the Pva anomaly, more associated with the Rossby wave breaking. It's also showing a good relation. So in a way, the general thing is that yes, we confirm that there is a quite a close link between large scale and extreme, and this is something good. I think that we can use in the forecasting methods more, and we can develop methods based on these relations. But let's go and look now at the different what's happening in the different classes. So are the different classes different only by the process that is generating the rain, or there is a difference also in the large scale that is forcing these classes? So this is another question to answer. So and to do so, we had to look at quite a few different type of plots and approach, and here I can show only a brief synthesis, but you can also check this. It will be in part 2 that is now under revision and should be hopefully come out soon. So we see, well, the first answer to this is yes, the large scale is also show some differences between the classes. So the events are different, not only because category 1 is occurring in winter, maybe there is a little bit less energy. No, it's different. Also the large scale that is leading to the trough in that position is also different compared to the what is happening in category 2. And this is an Moeller plot that shows the meridional wind anomaly, the meridional wind component anomaly at jet level. So it's basically, yeah, you can trace back. You can see and from this plot you see that you can. This is the composite over each over the extreme precipitation event in each category. So category 1, category 2, category 3. So you can see that in category 1 you can recognize a Rossby wave packet starting from remote from the Pacific almost. And T0, with T0 we indicated the trough associated with the stream precipitation. And you see the trough is basically here, and you on the forward side you have a strong southerly flow. So this yellow, it means that you have a very strong positive component, and here you have a very strong negative component. So the trough is in the middle. Here you have quite a extended high pressure, and then you have the upstream trough over the Atlantic, and then even the upstream again over the west coast of US or the Pacific. But this composite remains quite visible and significant up to 4 to 6 days before. While in category 2, the situation is seems to be more local and really something that starts on the east coast of the US and then produces such a strong flow downstream. So it's really a shorter wave packet, and the reason can be both. It can be two. It can be that before you have, of course, a Rossby wave packet or propagating, but there may be some cancellation due to phase cancellation, or this can be really an amplification that starts locally over the Atlantic. And a little bit also category 3 is more similar to category 2 rather than category 1. So to try to understand a little bit more, we did, as I said, different things. This is another visualization in which we, again, for category 1, category 2, category 3, we look at the composites over of geopotential height and geopotential anomalies in green, and integrated water vapor transport. And we marked also the position of the upstream trough, because this we wanted really to see if there were differences in the amplification over the Atlantic. And okay, so here you have to be careful, because the dashed line means geopotential anomaly, positive geopotential anomaly. Usually is the other way around, but so here is positive. So okay, so if we start from here, so 4 days before category 1 events, you see you have generally a kind of zonal flow with some previous negative anomaly from previous systems, but here you don't have anything basically. So all the downstream development start when a signal enters from the west and makes this trough deepening, so that the integrated water vapor transport basically increase in response to this deepening. This produces an amplification of the anticyclone, and then the next day a strong deepening of the trough here. In category 2, even at day 4, so 4 days before, you have kind of presence of integrated water vapor transport already before you notice a really significant trough appearing here. So it seems that this feature was present already, and was also trying to build a ridge in here. So and you can see also at day 2 the amplification of the ridge and the transport of in the Atlantic it's much stronger than in category 1, and you get also a stronger trough. So in over Europe. So in the end, from this view, you get the idea that the downstream development in category 2 is stronger. And in category 3, I mean, it's similar to, again, to category 2, but weaker in intensity. I don't have time now to show also a nice analysis that we include in this second paper based on PV tendency framework, in which we analyzed the different behavior in these 3 categories. And what we noticed that in category 2, the latent heating release over the Atlantic is stronger, and this produces stronger baroclinic coupling and stronger divergent outflow. So in this schema, we sketch what we think is the main mechanism. So if you increase the baroclinic coupling and the divergent outflow in this region here over the Atlantic, of course you put on the upper level very low PV anomaly that reinforce the development of the anticyclone over the Atlantic, and then produce an even stronger induce an even stronger trough downstream, so or a PV streamer in other words. And this chain of events could explain, or is typical, not could explain, is typical of category 2 events. So yeah, so this in few words, but of course the analysis was a little bit more complicated than this, but it's nicely showing that this may be true, in fact. So these events are really characterized by really strong integrated water vapor transport in the Atlantic in the first place, and then this induce the trough, and this again another strong flow of water vapor into the Alps. So it's a kind of it's a kind of a sequence of events that are almost rather inducing this. Finally, the last part is about predictability. These 2 slides that I'm going to show are based on results that are not yet consolidated, but simply I wanted to show them because I think are interesting anyway, but also because it's to complete this idea, to close our research. So going from extreme, understanding the dynamics behind that, and see if these different dynamics can be used as a justification for different predictability observed. And so I use a metric here. So what do we do now? We look at the predictability of the precipitation aggregated over the warning areas, and to evaluate the predictability, we use the normalized spread. So we use an ensemble, and we use the normalized spread of the precipitation, the average precipitation over these warning areas. The normalized spread is, the definition of normalized spread is the interquartile range of the 24-hour precipitation aggregated over the warning areas divided by the median. And we tend, values above, so much greater than 1 are indicating that the spread is too large to give any reliable or usable information, while if the values are smaller than 1, then the spread is it's smaller compared to the value of the median, so there is a strong signal in there. Okay, so it's a kind of empirical index that we can use to evaluate the predictability through the forecast ranges. So what is so the numbers here are based on the USNWF reforecast. That is a small ensemble that runs over the last 24 years, twice a week. So that was one of the way which we think we could investigate our list of events, because first of all, I don't think that there is a deterministic forecast in ERA 5 that we can use, but also we wanted to use an ensemble to have the estimate of the predictability. And for any of this forecast step, we have it's computed over 30-40 cases according to the forecast step, because the reforecast is not done every day, it's done only twice per week. So according to the step that you use, you can have a slightly different frequency. But anyway, 30-40 cases for each class, I would say, is not bad at the moment. And a bit the surprising thing is that if you look at category 1, you see a really fast growth of a fast loss of predictability, basically faster than category 2, that you would expect, since category 2 and category 3 include deep convection. You would expect to have kind of quicker loss of predictability, while this actually is observed, especially at the beginning in category 1. That was a bit unexpected, I will say. But one of the reasons of this could be that in the first steps, if the situation is in the large scale, produce a very strong integrated water vapor transport towards the region, then the orography may play an important role in maintaining, in lowering the loss of predictability in the forecast, because you know that for the orographic enhancement you will have precipitation over the orography. And in fact, you see that if you score only the mountain areas, you get better scores. And especially this is also occurring in category 3, that are mostly due to convection. Of course, because they probably for this close linkage between orographic initiation of convection close to the orography. But as I said, I mean, I don't spend too much time on this. I think it's really it's something that really interests me to understand more about this, but we still have to work a bit on this one. Another nice view about the different predictability in the different areas. It can be done through this kind of visualization, this heat map, where you see forecast steps on the y-axis, and you see all the areas on the y-axis. So you, in each box is colored according to this index. So where is yellow is good, where is blue it is bad. And you can see, for example, for category 2 events, this one that are characterized by very strong southerly flow. In general, over the western part of Italy, you have a very good, very good normalized precipitation spread that's good and stays good until 5 days before. While if you move towards more the central part of Italy, then you lose rapidly any predictability due to this less strict relation with the orography and the flow. And a bit also is happening in category 1. So I suspect that category 1, it's more there is a more a problem of the phase of the passage of the fronts, while in category 2 this is more stable, and if you have a stable flow and if you have the orography that is always there, you get a better signal. Okay, and that's the summary. So with we have seen many things. I tried to summarize. So we have a large data set of extremes. We have an objective method to categorize them, and the categories are well separated and appear to be meaningful in terms of different processes that we want to highlight. Category 2 is the one with that produced the largest effect, and due to this large scale and convection synergy. And EPE, so extremes are associated with Rossby wave packets, which mobilize water vapor plumes. PV tendencies and also other plots reveal that there are pronounced differences in dynamical processes among the categories. Category 1 are dominated by incoming waves from the Pacific, so there is a more continuous propagation of wave packets. So we can think that the wave guide in winter is more continuous, and you have while in category 2 it seems that there is a really a propagation that starts in the Atlantic and is really more controlled by the condition there. And category 2, there is also a stronger amplification, a stronger downstream development, and this may be due to the impact of the stronger latent heating release and divergent flow. Finally, for the predictability, the results are not yet consolidated, but there is this unexpected loss of predictability in category 1. And another thing that I haven't shown, but is also really interesting, we have computed the trend of IVT over the North Atlantic using year 5. The trend is highly significant, especially over the North Atlantic. And at the same time, we have observed an increase of a significant increase of category 2 and category 3 events from 1979 up to now. So these two things could be related, of course. I mean, if we think that all this argument that we have seen, that we have discussed, so the category 2 events are more due to this strong amplification over the Atlantic. If you increase the IVT over the Atlantic, then it's all consistent. But of course, this is just a supposition at the moment. We don't have any proof. Okay, thank you for listening, and sorry if I've been a little bit too long, perhaps.
Okay, thank you, Federico, for this excellent talk. So we have time, we're a bit late, but we have time for a few questions. So can you see the chat? Or maybe we can ask people to give, we can start with Roberto. Maybe Roberto can ask this question orally.
Yes, hi everyone. Can you hear me?
Yes.
Yes.
Okay, very good. So I have actually another question, but my first question was whether the reason why Cat 2 and Cat 3 events were developing, if you want to say, faster and more locally in the Atlantic is linked to the fact that these events occur in seasons when there is more water vapor available to deepen the development of this trough system. So it's another way, I wonder whether the latent heat release associated with moist processes, which are more frequent in the Cat2, Cat3 events, is the reason why you can trace back their development in the Atlantic and you don't see them coming from farther upstream. This is my question number one.
Yeah, I think, yes, I think there is a link between the two things. So the intensity, as we can call it, of the downstream development and the integrated water vapor transport in the Atlantic. But you know, with this classification, there is no notion, there is no explicit notion of seasonality inside. So we don't classify according to season. It's automatically classified. And this is a bit of the beauty of this, because it means that, let's suppose, for example, that in other season you get the same strength of the integrated water vapor transport. You can classify them according to this.
But you showed that in one of your first slides that Cat 1 happens mainly in winter and Cat 2 mainly.
No. It is like this. It is like this. Exactly as you said. In autumn, you have the condition where you have high sea surface temperature, for example, over the Atlantic. You have hurricane season going on. You have hurricane release of moisture in there. So you have a number of factors that are contributing to produce a lot of a very moist mass, air mass over there, and then to initiate this chain. But this happens also in the Pacific. It's not only something that doesn't happen on the Pacific. Simply for some reason, and probably the waveguide is not in the autumn. The waveguide and is not as continuous as in winter. You have a different propagation. So it looks like in autumn is a more local start.
Oops. Okay. We have a question from Linus.
So you already touched upon that there. So I first had a question whether the category 2 events, some of them are related to extratropical transition of tropical cyclones, and also the length or the climatological length of the Rossby wave packets, whether regardless of whether they produce extreme precipitation events, whether they are longer in the winter than in the autumn.
Yeah, so you're asking if there is a difference in the duration of these events. Yeah, so the yes, there is a difference. We haven't shown that. I think the category 2 events typically last about 2 days, while category 1 is shorter. So in winter is a bit short. They are shorter. Is slightly above 1 day. I don't remember now the exact numbers, but yeah, there is a difference.
Because I had the impression of your figure, but maybe it was just the examples that, no, it was from the composite that it looked like longer Rossby wave, life length of the Rossby wave packets in category 1 than category 2, and whether that had to do with that they happen more winter time than autumn time.
Yeah, in fact, I'm not totally sure. I mean, I have to check this. And I don't remember now the figures of the length, but that I remember. The only thing that I remember is that it's. I mean, there is a difference. There is a difference. in terms of length, yes.
Okay, thank you. Next question from Magdalena.
Hello, Federico.
Hello.
Excellent talk. Thank you very much. I've enjoyed it very much. I was thinking from the point of view of predictability, not at the medium range, but at the extended and seasonal range. I mean, I got my interest went into the category 2. Do you know if there is any, or are you planning to do any analysis of whether this category 2, the interannual variabilities of category 2 are linked to any climate predictor? You have mentioned trends, but it could be interannual variability over the Atlantic, for instance, and maybe linked to the abundance of tropical cyclones, or so that's from the seasonal point of view, but also from the extended range point of view, whether there are links to MGO phases or links to the weather regimes, the standard weather regimes.
Yeah.
So is there any weather regime more favorable to these ones?
No, I don't know the answer, because we wanted to have a small section about trends in this second paper, the paper about the dynamics of these events. But yeah, since you pointed out, I mean, there are many questions to be answered, so we couldn't basically. That was too short, and we look only at the trend of the IVT and the trend of the extremes, without looking at in more detail of the interannual variability and other linkages. So we decided to postpone this part to a different work that we still have to finish. So I don't know exactly. But it's a good question. I mean, we should, would be nice to investigate this.
Okay, now we take the last question. It's another question from Roberto.
Yes, hi, thank you, Frederick. So again, on predictability, I wonder, given the different characteristics of cut 2, 3 versus 1 in terms of the intensity and of precip and location, I wonder whether the index you used is enough to really make some consideration on the predictability of the different events. I suggest that you look also at a larger scale index, something linked more to the shape of a trough, intensity of a trough, and so on. Because as you said, I think I would expect, given what you showed, that cut 1 should be more predictable. No, so I think I would definitely do an analysis also at the large scale flow level, not just at precip.
Yeah, no, you are completely right. Yes, actually, thanks for the pointing this out, because we that was one of the plan, of course. And I first, before doing this, I did some specific test case, and I was scoring the precipitation and the IVT, for example, and IVT was much better than precipitation. So this is a kind of large scale indicator. Then you can go even more upscale and look at the wave itself, as you said. That's exactly what we would like to do in this in a new proposal and in the new ideas that we are now drafting about this. For these computations, that I did for the longer statistics that I did for precipitation, the plan was also to do something similar for IVT, using, for example, also a matrix that David Levers has used. So instead of using the spread, using the kind of correlation between averages over different areas. But we haven't done yet. But IVT should be much better. I mean, also David Levers has shown that it can be in the order of days You can gain 1 or 2 days of predictability if you look at of course, the large scale component. Yes.
Okay. On the really last one by Maddalena.
Well, this is not a question, it's just a comment in case it helps. I mean, I don't know whether the IVT over this Atlantic region of the States is related to the local SSTs. I don't know if it's related. I mean, there has been mentioned that these regions of the western boundary currents are really hottest spots for focalizing and amplifying the climate change signal. So, I mean, it's just a comment, really.
Yeah, that's in fact, I mean, it's surprisingly, because if you, I don't have now the map here, but if you look at, we produced the map of the IVT trend, and the significant part of this map seems to overlay to this region, so to the western boundary current part. So, of course, IVT has 2 components, humidity and transport. So if you have higher IVT, it means that one of the 2 it's bigger. But yeah, so can be both or can be one, but yeah.
Okay, so thank you very much again, Federico. I can see there's some new questions. Maybe you can reply to them in the chat. Okay. Or offline. But again, thank you very much for this excellent talk.
Okay, thank you to all of you, and yeah, I hope to see you soon. I know that is a bit kind of rhetoric sentence, but in this situation. Okay, thank you.
Okay, goodbye.
Bye-bye. Bye.